Welcome. In this lesson, we are going to be reviewing all of our transformations. And in the next lesson, we're going to be combining all those transformations. So how are translations used in a marching band show? The sights and pageantry of a marching band performance can add to the excitement of a sporting event. Band members dedicate a lot of time and energy to learning the music as well as the movements required for a performance. The movements of each band member as they progress through the show are examples of translations. So if they're moving along a line, that would be a translation. Also, we have another type of movement that you will see if you watch a marching band show, and that is rotations. And we're going to see a rotation when band members turn. Marching band, we call that pivot. Right? So when you literally step and you turn on one foot, you pivot on one foot and you move in a different direction. That's a rotation. Right? Or in marching band terms, pivot. Right? Notice, by the way, in the picture there, you can see the marching band members forming an S. What could S stand for? Why, of course, it must stand for Syracuse University. Go Orange. All right, let's review all of our transformations. But first, this is in your notes, let's start off with some vocabulary that applies to transformations in general. All right, so I want you to think of the words before I write them down. And to help you, I'm going to write the first letter. And so you think. See if you get it before I write it down. And you be thinking there. All right, so transformations in the coordinate plane. A blank is a change in the blank or blank of a figure. Blank, blank, or blank of a figure. That's a lot of blanks. So you might need a starting letter. I will tell you that word starts with a T. Now, the next three words, I really could order them in any way. However, I'm going to put P first. I'm going to put O second, and I'm going to put S third, because we haven't done S yet. So a blank is a change. What could T possibly be referring to? Well, since we are reviewing vocabulary related to transformations, perhaps T stands for transformation, and it does. So you can fill that one in your notes. A transformation is a change in the P. What's one thing that could change when we have a transformation? Actually, if you look below at the picture that's also in your notes, you see an example of P changing. Notice the pre-image is moving to the image. And what's changing? Its position. Sometimes when we perform a transformation, our figure is not facing the same direction. So what's that O vocabulary word? That where your figure is not facing the same direction, what's changing? Why, it's orientation. So the orientation can change. Your figure can be facing another direction. And the only one we haven't done yet is one that we'll do when we get to dilations, which is next quarter. And that's size. A size of the figure can change. The original figure is called the, well, hopefully you can figure that out because it's written on the picture below. The original figure is the pre-image. And of course, the resulting figure is called the image. A transformation, blank the pre-image to the image. Do you remember that vocabulary word that we use to describe what happens? What are we doing? Starts with M. A transformation maps the pre-image to the image. Did you get that one? I also want to add something to your notes that relates to maps, and it's another vocabulary word. So in your notes, and there's a whole big space there, and you can write like giant-sized, and you'd have room. Write the word superimpose. What does superimpose mean? It means to move one figure to another, so that they match exactly. So if you superimpose, so when we map the pre-image to the image, we are superimposing the pre-image to the image. We're moving one figure to the other so that they match exactly. Arrow notation is used to describe a transformation. And what would we call those little symbols so that we can distinguish between who's the pre-image and who's the image? Well, they're called prime marks. I went to write my P and it came out all funny looking. Prime marks are used to label the image, right? So we would say, so for instance, we have ABC becomes or maps to A prime, B prime, C prime, right? We just call it prime. All right, so a little review of transformations. We're going to go through all the different transformations very quickly. Notice, you will notice when I change the page that this is not in your notes. And that's because this is a review. You already have notes on all of these, and we're going to sum it up in that little handy dandy box there. So rather than giving you all these different images, I just gave you the summary one. So each reflections in the coordinate plane, each point of a reflected image is the same distance from the line of reflection as the corresponding point on the original figure. Remember that our line of reflection and you don't have to write this down because it's in your notes, unless you want to, just have it again. Line of reflection is and actually when I say in your notes, it's in the previous notes, is a perpendicular bisector of point on the pre-image. Actually, excuse me, I forgot to write the word segment. So a bisector of the segment. As I'm talking as fast, I slowed down my talking so it matched my writing, and by the time I got to write it, I forgot to say the word segment. So it's a bisector of a segment connecting, and I'll shorten this part up, corresponding, but I'll try to make it so you can read it, corresponding points on the pre-image and image. All right, so a little reminder there. And so in other words, your line of reflection lies directly in the middle between the figure and its image. So I'm actually going to show that by noting these are the exact same distances, and this would be a right angle. And we have some different lines that we've talked about reflecting over. So reflection of the x-axis, a reflection of a point over the x-axis is shown, right? So the pre-image is 2, 3. The image is 2, -3, and we know that by the prime mark. A rule for a reflection over the x-axis is xy maps to x negative y. So the x stays the same, the y is the opposite. And so actually whenever you reflect over a horizontal line, the x will not change, only the y will change. And if it's the x-axis, then the y is going to be the opposite. Now we have a reflection of a point over the y-axis. So the pre-image is 2, 3. Image is -2, 3. The rule for reflection over the y-axis, xy maps to -xy. So this time it's the x that's the opposite and the y stays the same. And matter of fact, anytime you reflect over a vertical line, the y will not change, the x will change. If that vertical line is the y-axis, then the x will become the opposite. Reflection in the line y equals x. Right? So to keep those distances, to be able to keep those distances from that line of reflection the same, X and Y will switch. And if you remember when we were looking at dot paper and not coordinates, we would look at the horizontal becomes the vertical, right? Or you could, go diagonal. So if I go diagonal, 1, 2, whoops, I find it harder to do that, 3, 4, 5, right? So I went diagonal, right? So my horizontal and vertical distances switch, so X and Y switches. I am going to get rid of this though. I'll leave the green up. And then of course we had a reflection over the line y equals negative x. Right? So same idea, that x and y are going to switch, but this time they're also negated. I think I'm becoming the opposite. And why do they become the opposite? Well, here, if I'm in the first quadrant, my x and y are both positive. If I reflect over that line, x and y are both negative, right? So not only will the x and y switch, but they'll change signs if it's a reflection over the line y equals negative x. All right, so you have this in your notes, except you don't have the little graphs. If you want, no, that's not a bad idea, but I didn't put the graphs in here. I guess I could have. If you want, you can grab a piece of graph, grab a piece of graph paper, and just stick 2 coordinate planes on there. I'm just going to illustrate the in that rotations box, the different rotations, because I think it can be a little confusing. Even though it's very, very helpful in terms of having a handy way to refer to the rules, it might be a little confusing if you're just looking at xy maps to negative yx and xy maps to negative xy and so forth. If I draw it to, I think maybe that'll click in your head a little bit more. But let's start off anyhow with reflections. I guess I'll write in red because that box is red. Now you have 3 of them up there, but we're going to add a couple more to them. All right, so we have reflecting over the y-axis, xy maps to negative xy. Reflection over the x-axis, xy maps to x negative y. And then y equals x. xy maps to yx. Notice we don't have a couple of them there. Let's include y equals negative x. Right, so xy maps to negative y, negative x. We also don't have our just generic horizontal and vertical lines. Right, so y equals c, and I'm going to note here that c means constant. Any number at all. Right, y equals c, and as a reminder, that's horizontal. xy will map to, all right, so now it's a little harder for me to write this, right, because it's not just a sign change if that's not the x-axis. So just as a reminder that x stays the same. So I'm just going to put x, right? So x with not writing anything means x is going to stay the same. Y changes. What does it change to? Well, it depends what your line of reflection is. And it depends what your point was. Right? But it will change if that's a horizontal line. And then we have x equals c. And then xy maps to. This time x changes, but not y. Y will stay exactly the same. Right? So those are all of our reflections. Dilations is in here because, well, that's what we'll be going to next quarter. So it's not right at the beginning, but it's helpful to have dilations in here. All right, so for dilations, we multiply the x and y values by a factor. All right, and I will tell you, we can just add this in here. When we do that, so we're going to use a matrix. And so our factor here is k. That's why it has a dk there. That little k is our factor, and so this is just a little preview. We're going to take k and multiply by the matrix of all of our points. And it'd be helpful if that word matrix looked exactly like it should. We'll just put it over there. Right, so we're going to create a matrix. Right, and all the matrix is just our points. Right, x in the x on top, y on the bottom, and when we do that, we can just multiply everybody at the same time. It's super easy. Right, and then we'll get our new points for our dilation. All right, so we're going to move down because that's all we're going to say about dilation, because that was just a little preview there. Translations, we're going to add a to every x value, add b to every y value. That's what this little symbol there means. And we had a way to write it in coordinate notation. xy maps to x plus a, y plus b. And again, here we used a matrix, and we also used a vector. Right? And I think that's all we need to say about translations right now. Lastly, let's go to rotations, and that's the one I want to illustrate for you. All right, so we're going to have, I guess I'll write in green again, since both boxes are kind of greenish. I'm going to use, and I'll use purple for the top box, so it doesn't look exactly the same. So that top box there, we're going to do the counterclockwise. And that's just because, well, that's first. And then we have the clockwise. Oops, and I'm going to write that in green. Okay, so this is going to be counterclockwise first, clockwise second. All right, so remember the sign here of our x and y. These are both positive. In the second, this is the first quadrant. Second quadrant, and we go, when we name the quadrants, we go counterclockwise. The x is negative, the y is positive. Third quadrant, they're both negative. Fourth quadrant, the x is positive and the y is negative. All right, so we're going to just have some random point, doesn't really matter. Here we are. All right, so that happens to be the point 1, 2, 3, 1, 2, 3, 4, 5. All right, so we'll just start right there. All right, if we rotate 90 degrees counterclockwise, all right, so if we're going counterclockwise, just a little reminder here, counterclockwise will look like this. It's opposite the way the hands on the clock go. All right, so we're going to go to our second quadrant, which is the one with a negative positive. All right, and my x and y will switch. The y is going to become negative. Why will the y become negative? Well, once they switched, y is now my x coordinate for my point. And all my x's in the second quadrant are negative. Right? So then we're going to have the point negative 5, 3. And I am now counting it right here. Right? So this would be negative 5, 3. And this is a 90-degree rotation. If we rotate another 90 degrees, it's going to be 180 degrees. They would switch back, right? Because we rotated another 90. Every time we rotate 90 degrees, they switch places. All right, so once they switch back, we're going to have x, y again. But now both x and y are negative. Well, why are they both negative? Well, because in the third quadrant, both x and y are negative. That's why. So we're going to have 1, 2, negative 3, 5, right here. All right, so that's going to be the point negative 3, negative 5. And that's the whole reason that they switch signs is just because our quadrants, our coordinate plane, the signs switch as we go around the quadrants. All right, and this is 180 degrees. And if I keep going, I'll rotate another 90 degrees. That would be 270. They'd switch back. My x's are positive, my y is negative. So when I switch back, right, so now what was x now becomes y, but it's got to be positive because x's are positive in that fourth quadrant. So 1, 2, 3, 4, 5, 1, 2, 3. but the y's are negative. So this is the point 5, negative 3. And this is 270. So notice there, it doesn't form a square because then they would be rotating around a circle. They'd be making these weird turns. It's just a nice little circle as it rotates around. And this, of course, was our point of rotation because this is around the origin. The same thing would apply. I'll just put P, not P-O-R, P of R, point of rotation. The same thing would apply if we were rotating around some other point, but we'd have to count the distances because the coordinates wouldn't mean anything. All right, so now we're going to continue on to the next one. Now we're going counterclockwise. So clockwise, that's just the way the clock goes, right? So clockwise is this direction. And we'll still start off with that same point. 1, 2, 3, 1, 2, 3, 4, 5. Because, well, that was just a perfectly fine point. All right, so if we go 90 degrees, oh, let me put the signs in again. They're both positive, then negative, positive, and then negative, negative, and positive, negative. All right, so now I'm not going to go to the second quadrant. I'm going to go to the fourth quadrant if I'm going clockwise. All right, and so X and Y will switch. 5 and 3 switch. X is positive, so 5 is going to be positive, but the Y is negative. So we're going to have a negative, right? So that's why we have Y negative X, because then my X is now my Y coordinate, and the Y coordinates are negative in that fourth quadrant. So this would now be 1, 2, 3, 4, 5. Oops. I think that's 5. It's a little hard to look at from my point. And I'm stretching as much as I can because of my microphone. So this is 5, negative 3. If we rotate 180 degrees clockwise, this is the same thing as rotating 180 degrees counterclockwise, and it's going to be, they would switch back, and 1, 2, 3, they'd be over here in the fourth quadrant where everything is negative. 1, 2, 3, 4, 5. I hope I counted that right. And this is the point negative 3, negative 5. Rotate one more time. Right? The X, they're going to switch. So the 5 will be first, 3 second. And the X's are negative, but the Y's are positive. So it's not going to be negative 5, negative 3. No, it's going to be 1, 2, 3, 4, 5, negative 5, 1, 2, 3. So if you have any trouble with those negatives, just think of the sign of the quadrant and you'll be fine. Oh, and by the way, this one was 90. This was 180. And now this is 270. We end up here. And that's the point negative 5, 3. So a 9 degrees clockwise is the same as 90 degrees, well, 90 degrees clockwise is the same as 270 counter and vice versa. And 180, well, that's just 180. So those little helpful hints, those little formulas there are just to help you to remember what's happening to X and Y each time and how the signs are changing. But I'm not expecting you to memorize that list at all. You should remember the reflections, right? But even as you do the reflections, it'd be kind of obvious. You reflect over X, the Y is going to change, and so forth. But just remember that the X and Y's change on the rotation. Use the signs of each of the quadrants to help you figure out who's negative and who's positive. All right? That's the easiest way. And now you've gone over all of ours, and I think that's the last thing for, oh no, this is not the last thing for this podcast. This is. So this isn't in your notes. Yeah, this is the last thing. This isn't in your notes. It's just a handy dandy way to distinguish between reflection and rotation. So maybe I give you the points and I ask you, what kind of transformation is this? Translation, students are usually fine on. It's reflection and rotation. They get them mixed up, especially if I just give you points. All right, so here let's look at 4, negative 5 maps to negative 4, negative 5. Right? Well, they're not switching, right? So it's not a rotation. Matter of fact, the only thing that changed was the sign of 4. Well, if just one sign changes, not both, they don't switch, it's a reflection. And in this case, since X changed and not Y, it's a reflection over the Y-axis. Right? So reflection over the Y-axis, the X value becomes the opposite, Y value stays the same. Right? So if only one sign changes, it's a reflection. Oops. We have 4, negative 5 maps to negative 5, negative 4. They're switched. They're opposite. But that could be two things, right? That could be a rotation, or that could be a reflection over y equals x, right? They switch for that too. Well, how can we tell the difference? Well, if you notice, 4, negative 5 is not negative 5, 4. The signs, one sign changed and one sign didn't. So if they don't just switch and stay the same, or switch and both negate, and only one changes, it's got to be a rotation. Right? Rotation, they switch and one changes. Now, if you look back to this little handy dandy little word, is it organizer? Here, I don't know what to call it. Under rotations, x y negative y x, x y negative x negative y. They both changed, but they didn't switch. X, y, y, negative x. All right, so notice that one only is changing signs each time. Or if it's 180, they're not changing because they changed for the 90, they came back for the 180, but the signs switched. Right? So if only one is switching signs and x and y is switching and only one changed signs, it's got to be a rotation. Now you just got to remember which one. Now if you can't remember it, just grab yourself a little coordinate plane, right, and look at it. All right, so it's either 90 degrees clockwise. All right, we're going clockwise from the 4th to the 3rd, or 270 degrees counterclockwise. So if x and y switch and one changes signs, the second coordinate becomes opposite. The first coordinate becomes opposite. It has to be 90, 270. So it's 90 clockwise. So either way, if they switch and one changes, it's 90 or 270. If it's the second coordinate that changes, then it's 90 degrees clockwise, 270 counterclockwise. And by the second, we mean the second in the image. If the first coordinate becomes the opposite, that's just the other direction. Same rotation, 90 or 270, just went the other way. You can always graph it too to help you out. All right, so what if we have 4, negative 5, negative 5, 4? Notice they just switched. If they just switch places, it's a reflection over y equals x. And now we have 4, negative 5, negative 4, 5. If both x and y switch signs and they don't switch places, then it's a 180 degree rotation. And if they switch and change signs, so if they just change signs, it's a 180 degree rotation. If they change signs and switch, then it's a reflection over y equals negative x. I didn't put this in your notes, however, it will get posted. And so if you find this helpful, you always print this out too. All right, that is the end of my podcast. In the next podcast, we are going to look at composite transformations. Thanks for watching. Bye for now.